Yeah. So we're all familiar with um, measuring angles in degrees. As a matter of fact, some older textbooks you'll see an angle probably written like this. You have an angle measured, let's say 30 degrees, and you'll have maybe some final breakdown of the angle, and you'll have maybe 20, and you have two little things like this, minutes, right? And then you have 10 seconds, right? So I think this came from the Babylonians, their way of measuring angles, right? So they have seconds, minutes, and then degrees. And just like how you would say 60 seconds make 1 minute, 60 minutes make 1 degree, right? Not an hour, right? So you say 60 minutes make 1 degree. So that's the whole thing. I think most of your trigonometric knowledge is based on this way of measuring angles, right? And if you say that there once two line segments meet somehow, there's some angle between them there, right? There's some angle between there, right? Yeah. However, as time went by, and this just goes to show how, in which class I was talking with, as I was asking them about their students and whether they think their students can create new mathematics, and the teachers gave me some surprising answers, But it's interesting to know how, over time, new mathematics have been created to be able to deal with new situations and problems that were unsolved before. They could now be solved with new mathematics. And then after measuring angles in degrees, right, so we had this measuring angles in degrees. Oh, too many E's, right? Yeah. There came radian measure of angles, right? The radian measure of angles basically was defined this way. And if you have a, let's see, this is L and this is R. The angle in the center there, right? Angle in the center there is equals to L over R, right? And this angle, this definition of this angle is the angle in radians, right? It's the ratio of the length of the line, the arc, sorry, the ratio of the arc over the radius, right? And whatever that works out to be is the angle in the center here. But you no longer refer to it as, alpha degrees, but alpha radians. And I think there's a symbol they use in a little c. I know you might think it's a little r, but it's a little c there. I don't know why they use a c rather than an r. Right? So this is another way of measuring angles. As a matter of fact, this measure of angles is what is used largely in calculus. All the findings in calculus are applicable, or they're valid for angles measured in radians, right? And when you get into calculus, there's going to be this thing called a small change, right? Small, that's basically what calculus is, small change in x and so on. Because calculus is built on this assumption, okay, so somebody is saying I'm not seeing anything, just a blank whiteboard. Is that the case with everybody else?
No.
Everybody else is seeing what I'm writing because I wrote some things on this whiteboard.
Yes, sir.
You seeing?
Yes, sir.
Yes, sir.
But somebody is telling me they're not seeing that. Oh, Alicia is saying she's not seeing anything. She's seeing just a blank whiteboard. That's strange. Alicia, I can't answer that technical problem. Because everybody else is seeing the whiteboard. But I'm seeing Alicia, Passad, Armagan, or Corsa is moving on the whiteboard.
Sorry, the board is blank with dotted stuff. I'm not seeing any other stuff.
Write something on it. Let's just make a scratch somewhere. Not seeing you writing anything.
But I'm not seeing anything other than that.
Are you on a computer?
No, sir, phone.
Oh no, my, that thing is going to be so small. What if I use all right. Let me try using Microsoft one. We'll see what happens. We'll see that. Tell me if you're seeing this. Are you
Yes,
seeing a
sir.
blank?
Yes,
Huh?
yes.
You're seeing that one.
Yeah.
So I'm going to write something, right? So we started to talk about that. We started to talk about no, I am going to record this. I am recording the session, right? Am I not?
Yes, sir.
Yeah, I'll share it with the rest of the class. Yeah. Yeah, so we were talking about. All right, give me a second. We were talking about radian motion of angles, right? Yeah, we're saying that that is defined as, the ratio of the length of the arc over the radius, right? And this measure of angles takes on greater importance in the study of calculus. Because in calculus, there's that assumption that when you're dealing with small changes, right? A lot of the findings were based on a small change taking place. And you get into calculus, you get into all of that, right? And if you notice, like, okay, we'll learn later on, just a moment, that let's say 30 degrees. 30 degrees is really what in radians 5/6, right? I think so. Probably not going. So this is a big number. This is a very big number, but 5/6 is a very small number. Put it in your calculator and tell me what it is.
It's 0.52.
All right, roughly 0.5. All right, 0.5. You see? So this is the angular radiance. Notice how small it is. I'm talking about magnitude. Right? It's the same angular in magnitude, in a small number. And this here is 30. Right? Let's imagine. So because radian measure values, the magnitude is small. It lends itself to kind of analysis you do in calculus, and most of those findings, those formulas, and so we come up with in calculus are valid with angles are measured in radians. That's why radians take on so much importance in mathematics from the time of them being invented, you know. And you know, all the formulas, and so from this here you can see that, well, the length of a line segment is what well, if you were to I use alpha here, but I think your notes didn't use alpha, right? The length of the line segment is given by that. There's even a new formula. You're looking at anybody's, I have the notes handy. If you want to deal with the area of the sector, usually when you want to find the area sector, you do what? You say the area, and that's in degrees, right? What is it? You go with 5r squared times theta over 360, something like that, right?
Yes, sir.
Yeah, but I think when you're dealing with radians now, with radians, what's the formula we have here?
Half r squared theta.
R squared, yeah, good. You know, so there are new formulas, and so new ways of looking at things, right? And there's that conversion, you know, like they say, okay, we know that there's 360 degrees in a circle, but then we figure out that there are 2 pi radians in a circle as well. So they're equivalent, right? And there's a little reasoning how they got to this, right? Would you follow that reasoning in the textbook? How they got this relationship? Like, okay, what's the circumference of a circle? That's when you're measuring angles in degrees. What's the circumference of a circle?
Two pi radians.
No. When you're measuring angles in degrees, how do you calculate the circumference of a circle? You don't say 2 pi r, 2 pi r.
Yes, sir.
Yes, sir.
Yeah, right. So the understanding there is that the angle then in a circle, if you were to use radians now, alpha is equals to 2 pi r, which is the whole thing divided by r, right? I'm using this here, borrowing this formula. The angle then in a circle, if the whole circle is 2 pi r, then to get the angle in the whole circle, you have to divide by r. Isn't that what this is saying? The whole circumference, which is L now, is 2 pi r, and the radius is r, so it goes that way, right? And you end up with The angle in a circle in radians I'm talking about is 2 pi. You already know this. The angle in a circle is 360. So from that, you can actually get a relationship between how much is 1 degree. I'd say 1 degree would be equal to 2 pi over 360. I shouldn't be doing these kind of things, you know. Well, I wanted it, right? So you actually can have the relationship or kind of a conversion factor, right? So pi over 180, and from this you can get, if you do it the other way around, you can get 1 radian. I'm getting kind of overcrowded here now. So this is a nice conversion factor. So 1 degree is that. So we can go from here and get 1 radian equal to, what is it, 360 over 2 pi. So you get all that. Right? This is another conversion factor now for this is if you want to convert, let's say you want 30 degrees, you just multiply it by 30. You want 60 degrees, you just multiply that by 60. Or you want, convert some amount of radians to degrees, let's say 5 radians, you just multiply 180 over pi by 5, you know? So those are 2 nice conversion factors. And so it's all in the notes here, right? And I think there's some exercises to do some conversion, right? There were some nice examples too. So this is a nice couple of examples on where the angle is measured in radians, right? They're in the notes. I just want to go through them quickly. So they're telling you that there's a railway line, a train, right? A train on a track. They're talking about that. They're talking about a railway line. It changes direction by 20 degrees when passing along the circular arc, and the length of the arc is 500 meters, right? So this arc, this arc here, and it's kind of small, right? You see it's small. So the arc is from here to here is 500 meters, right? And you want to know what's the radius. So little geometry will tell us that if the arc here subtends an angle of 20 degrees, right? Oh, by the way, okay, if you measure the angle out here, tangent when let's say the train is here as compared to there, right? When you draw the 2 tangents, they will intersect at 20 degrees, right? And a little bit of geometry will tell you that would make the angle in the center here also 20 degrees, right? So when the train, or let's say you just stick to the railway line, when it makes that circular arc of 500 meters, the angle in the center, right, is just 20 degrees as well. And I wanted to find what's the radius of the arc, right? So we make use of the arc length formula. I think I can annotate on this diagram. Something like that. We're using the arc length formula here, right? And well, of course, you convert that 20 degree to radians because you're working with a formula that applies to radians only, right? And then you use your formula now. So this is the arc length, right? You don't know the radius, the angle that that was made by that arc with the center of the circle is pi over 9. So you just do some rearrangement of the formula and you get r equal 4,500 over pi. And you can see the arithmetic here, right? You take over the pi over 9, you divide 500 by it, so you have to flip it around, multiply, you get 5 by 9 on 500 by 9 over pi, right? That's your answer there. A simple, very, very simple problem involving the arc length formula. Let's take another one. Just clear all of this. Yeah, don't say mess up the notes. Formula. Yeah. So let's take a second one. So here you have chord AB divides a circle of radius 2 meters. These are big circles into 2 segments, right? And the chord subtends an angle of 60 degrees. That's what you're saying, right? They want you to find the area of the minor segment, right? And that's this little piece here. This little piece here, they want you to find. And it's just an exercise in using the formula, this formula here, right? I know you're used to that one where you go, what is it? Pi r squared by theta over 360. But no, you're not using that one because they want you to make use of the, well, I don't see them saying you should use this method, but if you're given a question like this, you would know what they want you to do. But the writer probably overlooked it to say specifically that you should use radian measure of angles and the formulas that are associated with radian measure of angles, right? Yeah, I think they didn't say that. Yeah, so 140 degrees, that's pi over 3 radians. And you use the formula pi r squared theta, that's the area of a sector. So you know what you do, right? You do the area of this, the whole sector, and then you do the area of the triangle. That's what you do. The area of the sector minus the area of the triangle will give you that little piece here, right? That's what's going on here, right? Find the area of the sector to be this. Find the area of the triangle, right? Notice we keep using the formula for area of a triangle in degrees, right? Because there isn't a kind of formula that you use. You could put, instead of sine 60 degrees, you could put sine of pi over 3 radians, but your calculator now has to be in radian mode. I don't know if you know what I'm talking about. You know, your calculator can be in degrees mode when you're working with radians, right? So you could do that. You could do that. Right? It's just that consciousness that you have to change the mode of the calculator. So you find the area of the triangle and you subtract 2, and this area is the area of the segment that you want, right? That's what you did there. Right? Yeah. This is a little more complicated example. Part 3 here. So they're talking about 2 discs. One has radius of 3. The other one has radius 4. They're such that their centers are 5 meters apart, 5 cm, sorry, apart. And they want you to find the perimeter of this thing, this big figure that's this form, right? All right, so this one a little more complicated. You're kind of extracting this triangle here. That's what they did there. And you have to find these angles in here. right? You have to find these angles in here, right? Notice they use the tangent ratio, and we found alpha to be that, beta to be that, right? This is this puzzling to you? These ratios that we're talking about here, tan alpha is 4/3. Then finding the angle, and notice you have for you to put, you can either put your calculator in radian mode and get this directly, or you could use your regular calculator, leave it in degrees mode. Change it, okay, get the angle in degrees and then change it to this, right? One and the two. Are you finding this puzzling?
No, sir.
Okay. You know why do they use this ratio here? This applies to right angle triangles only, right? The ratio, the sine, cosine, tangent ratio applies to right angles.
Yes, sir.
How
Yes,
do we
sir.
know this triangle is a right angle triangle? So I want to see if you all are paying attention.
3, 4, and 5 are square numbers, I think.
What?
So they're the Pythagorean triples.
Yeah. Well, that's a very concise answer. Yes, in that the lengths and the example, of course, the author wants to give you a simple example. So they use a Pythagorean triple, right? That will give you some really nice answers. So yeah, you got the angles, you realize then the angles in the same thing, you're double that, right? Twice, right? Because if you realize this triangle here and that triangle here will be identical, right? From that now, you can actually find well, the angles over here, right? So like this angle here, you can actually find that angle, and similarly, you can find this angle, right? That's what we did here. And with that now, you have the angle, you have the radii of both circles, right? And now you can actually find the length of the arc, right? Length of the arc formula, r theta. You use the formula for each circle, right? So you put this part here, right? And then this part here. You add them together, right? Simple as that. And you get the you get that there. So these are, I can go on and on, and you can look up so many examples of problems involving radian measure of angles, right? But with the basics, those conversion factors that we got, the basic formula, your background knowledge in trigonometry and geometry, all of that will come into place, and you can use those to solve any problem. Well, not any, but most problems that you will encounter, right? Good. So let's turn our attention now to the general angle, right? And we want to talk a little about the ratios, the sine, cosine, and tangent ratios, right? So let me share that the screen. Oh, why Microsoft wants to giving me the suggestion, wasting time. Yeah. So let's talk a little about the um, the general and the trigonometric functions, the trig functions for the general angle, right? Let's talk about that. All of you are familiar with trigonometric ratio when you have some right angle triangle, right? And if you have some angle there, theta, and you have some side, I think we call this the opposite side to the angle, right? Whether the adjacent side, the hypotenuse, and so on, right? And you define the sine of the angle, cosine of the angle, tangent of the angle, in terms of these three sides, right, of a right angle triangle. You remember that from your, you must be teaching that to students and so, right? Yeah, and then you went a little further, I think at CXC level, you use a unit circle, right? You use a unit circle here, from the center here. And you let this be one, you did some playing around with the unit circle and you were able to figure out the sine, cosine, and tangent of angles between 0 and 360, right? You remember that? I'm not hearing a response.
Yes, sir.
Yes, y'all gotta say something, Don't be cooking and if you're in this class, I'll be watching TV and all kinds of other things. Please be present 100% in this class. Yeah. And that's where you came up with, and you figure out that for angles between 0 and 360, all the what is it say, all silicon gaps, all the ratios are positive there, sine is positive here while the others are negative. Tangent is positive in the third quadrant, angle between 1 and 270. And then the last one went from 270 to 360. Cosine is positive, the others are negative, and so on. Right? So we want to enlarge, we want to kind of go a little further than we started out with acute angles here, angles between 0 and 90. We went on from angles from 0 to 360, so that's a nice, we're going a little further here, right? So we want to go out to angles that, regardless of what they are, what about an angle of 500 degrees? What about an angle of, 1,000 degrees? What is the sine of it? What is the cosine of it? What is the tangent of it? What about an angle that is negative 100, negative 1,000? What's the sine? What's the cosine? What's the tangent of such an angle? Right? So we want to go beyond what we were used to. Right? So I think erase this. I think I can erase this. Yeah, I'm gonna just erase this rather than getting a rewrite it all. There. So let's go back. So we came to realize that you can measure angles from, okay, let's say you have the coordinate axes here, right? X and Y. And if you were to measure an angle going this way, the angle is said to be positive, right? Positive angle. If you measure angles going this way, clockwise, you get negative angle, right? Or you were introduced to this before. And when you measure angles counterclockwise, the angles are positive. When we measure them clockwise, the negative angles.
Yes, sir.
So what we want to do, we want to expand our definition now to the general angle. We're not sticking to acute angles. We're not talking about just angle between 0 and 360. We're talking about any angle, whether it's 1,000 degrees or negative 1,000 degrees. You know? So let's say we take an angle. Just any angle. So the angle is, let's see here. All right. It's a fourth quadrant. So the associated x coordinate is there. The associated y coordinate is there, right? So you define the sign of that angle. Sign of theta 1. As a matter of fact, I should not use a, let me not use a subscript. I just want to give you a, okay, right? Yeah. Okay. The general definition really of the sign of the angle is y, and the segment here is r, whatever it is. It does not be 1, like you have here in software, right? Sine of the angle is y over r. The cosine of the angle is x over r. And the tangent of the angle, oh, I should say t, and I think that right in the sheet is y over x. And this definition is basically the general definition of the sine, cosine, tangent of an angle, regardless of where that angle is located, and whether the angle is positive or negative, it doesn't matter, right? And why we say that, you know, like okay, in the first quadrant here, if an angle is there, that angle could be 30 degrees, right? Because that's an angle in the first quadrant. It can be 390 degrees will also be right there. Think about it. You are to go anti-clockwise. You go from here, you go right the way around here, you reach back here. You get 360. Plus another 30 degrees will give you what? 390, right? So again, the sine of such an angle will be that. The cosine will be that, and the tan will be that. And you will notice that any angle that falls in the first quadrant, it will be a negative angle going this way, you watch. This angle, let's say this angle here, not this one, right? This one, going right and the wrong way. So we start here and we go that way, right? This angle will be how much? Will it be negative 330 degrees?
Yes, sir.
Yeah.
Yes, sir.
The sine of such an angle will still be that, the cosine will still be that, the tangent will still be that. And you notice that the y coordinate is positive in the first quadrant. The x coordinate is positive in the first quadrant, and therefore the sine of such an angle, cosine of such an angle, and the tangent of such an angle will always be positive. Right? So here we're not talking about just acute angles. We're not talking about angles between 0 and 360. we're talking about angles that possibly is greater than 360, right? It could be negative angle, but once when we measure the angle, it falls into that first quadrant. Well, the ratios are defined by these here, right? And you notice that they will all be positive, right? So remember, this definition doesn't hold for just acute angles or angles between 0 and 360. No, they actually hold for any angle, the general angle, right? If we go a little further, maybe I can make this a little space here. So I'll go here. Then you take an angle in the second quadrant, right? So all right, let me go with the subscript, right? Good. So let's go with a second angle. Right? This angle is the second quadrant. Let's call it theta 2. And I am wrong to say, I mean, I started it when I put this here, right? So the associated x coordinate is going to be negative. The associated y coordinate is going to be positive. R is R, so it's going to be positive. So the sine of an angle here in that second quadrant, right, is y over r minus x over r, and the tangent is going to be y over x. Okay, that's only a negative, right? And that's really got that idea that the sine of the angle, second quadrant, is positive. Cosine is negative, and tan is negative. But remember, I know I did put an arrow from here, right? And you might want to think that I'm referring to just an angle from from 90 to 180, right? Because the angles in the second quadrant are like that. But we are not here talking or restricting ourselves to angles between 90 and 180. No. Any angle, right? So let's say you go right the way around here, that's 360 plus, let's say 120. How much is that? 360 plus 360.
480.
480, sir.
Okay, yeah, somebody is working their brain quickly here. So an angle of 480, that angle lands right here, somewhere here, right? See? This will be the sine, this will be the cosine of the tangent. Let's go negative. If you go this way, see this is negative 180. Let's say you add another 30 degrees, right? Or something like that. That'll work, 30 degrees. So you get what? Minus 180 minus 30 will be what? Minus 210. Let's say an angle of negative 210. Again, the sine, cosine, and tangent of those angles. At least with the sine, when I see the sine in front, is going to be the same, right? Sine is positive, the cosine is negative, the tangent is negative, right? And it's defined by, notice, sine of that angle is the associated y coordinate over the radius, right? Or the length of the line segment. I don't know what it's called. The cosine is going to be the negative associated exact x coordinate over r, and the tangent is, and the y is positive, but the x is negative, and that makes this whole expression negative, right? And we can continue that reasoning. I think it takes a pen down to see that. If you were to go in the third quadrant, you know, so you have some angle in the third quadrant, right? Let's just see. All right. That's theta 3. And I know, yes, you will charge me and see, I started to measure here, so I'm talking about the angle between 180 and 270, but I'm also saying that this applies to any angle you can apply this to a negative angle if you measure this way. So probably minus 100 degrees, right? Or if you were to measure this way, 360 plus maybe another one, what is that? Let's say 200 or 220, 240, right? You get a very big angle now, more than 360. It's still, the ratios remain the same, right? So the sine of theta 3 is, what is it? Minus y over r. Notice negative. Cosine of that angle is minus x over r, negative again. And the tangent of theta over 3 is minus y over minus x, which makes it positive, right? And that's why they have that thing that any angle in the third quadrant. Here we're not talking about just angles between 0 and 360. We're talking about any negative angle that falls there. Any positive angles that fall there greater than 360. These ratios hold, right? Sine is negative there, cosine is negative there, tangent is positive, right? And similarly, just go this last one because we came this far. Take an angle that is in the fourth quadrant, no? So one call that theta 4, yeah. Go back there, the associated its coordinate will be positive, the associated y coordinate will be negative. R is always positive. And you get the same theta 4 equal what would that be? Minus y over r cos of theta 4 is x over r tan of theta 4 is minus y over r, right? There's where you got that idea that in the fourth quadrant, cosine is positive. So these are negative, right? This is positive, those two are negative. And again, I'm reminding you that theta 4 need not be, let's say, an angle of, let's say this is 330. So it need not be, it could also be negative 60 degrees this way, right? And it could also be a very large positive angle that ends up in the fourth quadrant somehow, right? So keep that in mind that these ratios here, right, that the sine of any angle is the associated, what is it, the y coordinate over the length of the line segment, right? This is the line segment of buffer, right? Similarly, cosine of any angle is the associated x coordinate over the length of the line segment, right? And tan of any angle is the associated y coordinate over the associated x. Forgive me for using that one. Yeah, right. So that goes for any angle. It's not restricted to just acute angles. Angles between 0 and 360, but no, covers even negative angles, it covers angles that exceed 360 by far, right? Yeah. So we will want to turn our attention to a review of the sine and cosine rules that I think most of you are probably teaching that in school and so. I just wanted to highlight what they refer to as this has to do with the sine rule, right? The sine rule. The ambiguous case. Ambiguous case. Right? There's a nice example in the notes. Let me share that. Yeah. And this was the example I was referring to, right? I think in the CXC syllabus, they'll tell you not to cover the ambiguous case, right? Well, let's just deal with it. So they describe a triangle. You have this triangle. The angle inside there's an angle A that is 24 degrees. There's a side C that's 2.6, and yeah, the side opposite A is 1.1. So let's just say we draw a hypothetical situation, but we don't know what a triangle looks like. So there's a 24. There's a 24 degrees. Let's say this is 24 here. The side opposite is 1.1. So this is let's say this here is 2.6, right? Right. So you see, we assume that this here is nice, maybe an acute angle and all, right? So okay, we go through the process. They ask us to find C, right? They ask us to find C. That's this angle. This angle C, right? So you use your sine rule, and you get sine C equal to 0.96114. Now, you can have two possibilities, right? You can have the angle being 74 degrees, and you can have the angle being 106 degrees, right? By the way, you all know how we got these two angles. How will you get this force off? How will you get this force off? 74 degrees.
Sine inverse of 0.9614.
And you did that where? How you got the 74? You said inverse, so how will you get that? If the book had a blank space here, how will you get it? Hmm? You don't know how you get it 74?
Or use a calculator.
Exactly. It don't take so long to say that, huh? You use the calculator because we have an instrument. We have an instrument that can churn that out for us. Now, the big question is where we get a 106 from? Where we get a 106 from? Calculator doesn't give you that, though. How will you get that? How do you get that?
180 minus the 74.
And why are you doing that? Why are you doing that? Any thoughts? I think you all can annotate on this diagram if you want to, right? You just got a formula from somewhere. You know the reasoning behind it? Anybody know? Say no if you don't know, right? Or where you got the 180 minus 74, where you got that from? What's the basis of, that little procedure to subtract 74 from 180? Where do you get that from? We're not doing mathematics, right? We have to have a reason for what we're doing. No thoughts? Let's see. I'm sure you tell the students in school, subtract 74 1 here, 1 to 6, but you don't know why you're telling the students that. And well, what is this now? Y'all give me a second. Somebody light a big bonfire by me here now. No. Give me a second. Yes, we were here, right? And I was talking about this 106 here. This 106 here, right? And we were reasoning just now. I think I can actually write here too. Yeah. So if you have some angle, let's say 74 degrees, you see, right? And there's an associated y coordinate here, an r, such that y over r equal to 0.9614. That's what that is saying, right? But you are also seeing that there's another angle You see that? There's another angle. This is R. And this is Y. So there's another angle whose, so 74 is one angle whose ratio, the Y coordinate over R, is this. But there's another angle here. See? And using your little bit of geometry, and that's where that 180 minus 74 thing somebody talked about just now. There is another angle coming from here that goes there, right? Whose sine is also 0.9614. Do you see that? So while we might want to say, the calculator gives us 74, there is another angle there. As a matter of fact, there are infinite number of angles whose sine is 0.9614. Just to get that out to the beginning. Well, we were concerned here with a triangle, so we're sticking to angles that are less than 180. So here we have another angle from, if you measure it from here to here, whose y coordinate over r is also 0.9614. And that's where you got the 106 from, right? Somebody suggested we subtract 74 from 180. And that's because of some geometry here, right? We're not going to go through that. So now you have two values for C. You have C being 74 and C being 106. So we can discount the 106, right? We have to still see whether it can fit in a triangle, with the other details. And when you check it out, this is what happens, right? What do they say? Yeah, you can have a triangle where this angle is 24, this side is 2.6, right? And that angle is 106 or 74. Either of the two will fit the data that was given or the conditions that were given. So we can conclude that the answer was 74. It's possible that the answer could also be 106. You see? But oftentimes when you have these problems, you have to check because that second angle sometimes, when you notice they found the third angle in each case. You notice? They found the third angle. And the angle, when you add all of them up in the triangle, it is 180. There are times when you might have a second angle here that when you find this third angle, it doesn't work, right? And you might very well not be able to use it, right? So you just have to be careful, right? The whole idea is that don't discount that second angle right away, this 106, or whatever is another problem. Don't discount the second possibility right away. You have to check to see, right? Whether you can have another triangle with a second angle inside. So keep that in mind. Good. Next, we want to turn our attention to the graphs. So the graphs, I just want to, well, these are the graphs and their properties and so on. We can make this a little bigger. Yeah. This is what a sine graph looks like. Right? It's continuous. It goes on to infinity in both directions on the horizontal axis. So we don't have to stop at 3 pi or, or sorry, at 2 pi or minus 2 pi. We can go on and on and on and on. Right? You can have a million degrees. As we just said that we're not sticking to just acute angles or angles between 0 and 360. No, we're going negative. We're going beyond 360. Right? Yeah, these are some properties. You read up all about these, right? This is the cosine, and you must know the nature of the graph, right? Its amplitude, its domain, its range. You know all those characteristics. It's all here. Right? You need not go through them back. You can read. I know you can read, right? And then I think that's from your knowledge of just the graphs. You can know a lot of like, okay, what's the cosine of 0 degrees? You know, because you remember the graph, right? What's the cosine of 90 degrees? You know, what's the cosine of pi degree, pi radians? What am I saying? Yeah. And you notice they give you in terms of pi because they just want you to get used to using radians, get into that mode. Because you're used to degrees so much, right? You know what's the cosine of 3 pi over 2, which is 270. What's the cosine of 2 pi? Because you know what a graph looks like, So same thing with the tan graph. You can know, tan 0 what it is, tan 90 is undefined, tan of 180 is 0 again. So you can know those from the properties of the graph, right? And that's what we're talking about here. Then there is what you call the reciprocal, the minor trigonometric ratios, right? That's 1 over sine, 1 over cos, 1 over tan. What do you introduce to those? What do you call 1 over sine? What do you call that ratio? 1 over sine.
Cosec.
Yeah,
Cosecant.
cosecant. Yeah, well, we say for short, cosec. 1 over sine being secant or sec. And 1 over tan is cotangent or cot, right? And how to draw the graphs is like, once you know one, right, you can know the other. They're telling you how to draw, like the reciprocal of 0 is positive or negative. infinity. So if I were to go back, let me just go back to Rashi. So here, when it's 1, it's a maximum point. Here it's a maximum point. The 1 over cos graph will come something like this. Come something like this. You know, where it's heading to 0. Oh, sorry, I should put this up here. There's an asymptote down here, you know. There's an asymptote down here, right? And then where it's okay, it's going to a minimum there. Well, then from up here now, so it goes up. Let me see if I can use that. Oh, actually, there's the whole thing. So, yeah. So your graph should go like this, right? Where there's a 0 here, there's actually an asymptote there, right? Coming down and so on. So you actually make use of some basic, they explain some basic rules here when it comes to drawing reciprocal graphs, right? Some basic rules, right? They're telling you also continue here. All these are little rules. And you can actually see the graph here. So you have this is the sign. So okay, watch. It was 0 here, but it will come from infinity from up here, right? It's 1 there, so that's a maximum point. Here you don't have a minimum point. It's 0 there, so it go back to infinity, and you continue like that. Goes negative here, so it comes from negative infinity. It's a minimum there, so there's going to be a maximum there, and so on. It goes to 0 there, so it's going to go to negative infinity, right? So it's the very opposite there. That's what the graph says. That's how you draw it, right? And the same is true of the secant and the cotangent graphs, right? A good graphing program that, I forgot these here, the inverse circular functions as well. I go to that graphing program, right? And the inverse graphs looks like this, right? Get familiar because you'll need them in calculus, right? You'll need them in calculus. Maybe not so much in this course, but get familiar with it. These are the, so is our, this is our sine, this one here, right? This one is our cos, and this one is our tan. Very, very useful graphs in calculus. Right? Know their properties, get an idea of what they look like, and how they arrive at the graph. It's good for you to figure that out, right? I think you know all of this, how to figure out these common trigonometric ratios. I want to instead share some. Give me a second. I want to share a good graphing program that every one of you, if possible, can get familiar with. Yeah. Where am I? Desmos. Desmos is the program. Have you ever used this program before?
No, sir.
No, sir.
Hold on. What is this called? Yeah, this here. So like you want a sine graph. Y equal sine. You can go with theta, you can go with x. Let's go with x. Right? And maybe if you want to change, like, you see how they have this here, maybe you want to change You want to change the values to go for minus 360 to 360, you know, degrees, you know, what wrong with it? You could fool around with it, right? Yeah. You want y equal cos x, you know, that cos x y equal tan x, you know, it's all here. They give you different colors, you know. You want a straight line, y equal 2x plus 1, you know. Oh, okay, I'll use a bit more. Yeah, the line will not look, the line will not show well because of the sine and cosines, right? But you could draw in, you want a quadratic, y equal x squared. Yeah, because of the scale I'm using, the line and the quadratic will look very fun. X squared plus 4x plus 4. So you can actually graph anything. Remember, Desmos is it. Right, Desmos. You use this program a lot, this website a lot during this course. But so we did a nice review there of some basic trigonometry, right? And we're going to build on this now from now on in the course.